Welcome to The Explainer. Today, we are cracking open the modern engineer's toolkit, and I want you to forget the old cliches, because we're going to explore the essential software and hardware that are, quite literally, designing and building the world all around us.
So, let's just jump right in with a question to kind of challenge that classic image. When you picture an engineer, what tools pop into your head? Are we talking a hard hat and a wrench, or is it something else entirely?
For a lot of us, it's that classic image, right? All the physical tools. But the reality is, an engineer's most powerful assets have made this incredible leap from the workshop right onto the workstation. We're talking about the digital world of sophisticated software and super complex simulations.
And you know what's funny? Sometimes the most powerful tool isn't some super expensive, specialized piece of software. Check out this quote from a discussion between engineers. It really hits the nail on the head that great engineering isn't just about having the flashiest tools, it's about knowing how to use the right tool for the job. Okay, so first up, let's dive into our first discipline, the world of mechanical engineering. This is where physical products are born, everything from tiny little gears to absolutely massive engines. The absolute foundation, the bedrock of modern design is CAD. It stands for Computer-Aided Design. You can think of it as a digital drafting board on steroids. It's where engineers build these incredibly detailed 3D models. They see how all the parts fit and move together, and then boom, they can generate the 2D blueprints needed to actually make the thing. Now, not all CAD software is created equal. Different industries definitely have their favorites. Take CATIA, for instance. It's basically the heavyweight champion in the aerospace and automotive worlds, mostly because it's a beast at handling the kind of incredibly complex, curvy surfaces you'd find on a modern car or an airplane. So, you've designed your masterpiece in CAD, but will it break? You really want to know that before you spend a fortune building it. Well, that's where FEA, or finite element analysis, comes in. You can think of it as a virtual stress test, a digital crash test dummy for your parts. It lets you see if your design can handle real-world forces before it ever leaves the computer. And here's something that might surprise you. It's not all just clicking and dragging in a slick interface. Programming is becoming an absolutely crucial tool. More and more, engineers are using scripting languages like Python to do the heavy lifting in the background, automating complex calculations and sifting through mountains of data from simulations. It's the kind of work that would be completely impossible to do by hand. Okay, let's zoom way out now. We're going from individual machines to the massive infrastructure that shapes our cities. Welcome to the world of civil engineering. For civil engineers, the sense of scale is just immense. I mean, their software has to be able to manage the complexity of entire cities. They use these incredibly powerful platforms like Civil 3D to design and document everything from a simple road to a massive highway interchange, or even a whole new neighborhood. So, how in the world do you build a highway digitally? Well, it's a pretty logical, step-by-step process. First, you define the road's path from a bird's-eye view. That's the alignment. Then, you figure out the ups and downs, the hills and valleys. That's the profile. After that, you create a slice of the road, the lanes, the shoulders, the curbs. That's called the assembly. And finally, you stitch it all together to build the full 3D model, which is known as the corridor. And here's a crucial point. Civil engineering isn't just about building stuff. It's about deeply understanding the environment it's built in. That's why tools like GIS, Geographic Information Systems, are so critical. They allow engineers to analyze and map everything about a location, from soil types to floodplains to water supplies. All right, so we've gone from big machines to massive infrastructure. Now let's power down and zoom way in to the tiny components that run our entire digital world. Let's talk about the toolbox for electrical and computer engineering. What's so cool about this field is that it's a perfect balance of two different worlds. You have the tangible, hands-on work of building and testing circuits, but you also have this super abstract digital work of designing and simulating them in software first. To really succeed here, you've got to be a master of both. So let's start with the physical side. These little guys are jumper wires. They're pretty much the bread and butter for prototyping. They let an engineer quickly connect different components on a breadboard just to see if a new circuit idea actually works. Okay, stepping it up a bit, we've got these more robust cables. They're called banana head cables, and they're what you use to connect the serious lab equipment, like the power supplies that provide the juice and the multimeters that measure it. And finally, for that quick and dirty testing, you have alligator clips. These things are awesome. They let an engineer make a simple, temporary connection to a component without having to solder anything, which is perfect for troubleshooting and figuring out what's gone wrong. Now, let's switch over to the digital side, Because this is where the real magic happens. It's a category of software called EDA, or Electronic Design Automation. These are the tools that engineers use to design the intricate brains inside every single electronic device we use, from the microscopic integrated circuits to the printed circuit boards that hold it all together. It's the digital blueprint for all of our tech.
Okay, so from the circuits that power our world, let's zoom in even further, down to the very atoms that they're made of. We are now entering the fascinating field of materials science.
You can honestly think of materials scientists as detectives for matter. Their primary job is a process called characterization. They use these unbelievably advanced tools to analyze a material's structure and its properties, to understand exactly what it's made of and predict how it's going to behave.
And just to give you a sense of the insane scale they work at, get this. Materials scientists use tools like scanning electron microscopes that can magnify an object up to 500,000 times. That is powerful enough to literally see the arrangement of individual atoms. It's just mind-blowing.
Okay, so we've covered the tools of today across all these fields. But for our final section, let's look ahead. Let's explore the next generation of tools that are starting to reshape every single one of them.
This chart here from McKinsey tells a really fascinating story about where automation is having the biggest impact. For predictable, repetitive physical work, think of an assembly line, we can already automate nearly 80% of it. But the moment you introduce unpredictability, like on a construction site, that number just plummets down to 25%. It really shows you where the next big challenges are.
And this all leads us to one big final thought. As our tools keep getting smarter with AI and automation, and they start taking on more of the routine calculation and design work, what does the role of the human engineer become? It seems pretty clear that as our tools get smarter, well, the engineer has to get smarter too.